All right, let me make a note of the time. So this next part is optional. If you want to, in the YouTube, you can skip ahead if you don't want to look at damped and driving oscillations. But I think they're kind of fun and easy to display in Mathematica, which is kind of nice. Simple harmonic motion is nice and would occur forever because there's nothing to stop the motion, the restoring force, from making things slow down or whatnot. You could imagine, perhaps I have, the box hanging, vertically by a slinky, but it is, going through mud, as it oscillates up and down, rather than just doing it in the air where we might be able to treat friction as negligible. Maybe it's moving through mud as it oscillates. You're trying to, or maybe you treat air resistance as a friction. In that case, there's always a friction that's acting against the direction the box is moving. So that friction force damps the system. Eventually, the motion would get damped away because that's what friction wants to do, and the oscillations might trickle down to zero. So simple harmonic motion, and let's just think of this in 1D. Simple harmonic motion, we said, was described as the acceleration, or the second derivative of position, was equal to minus omega squared times the position. There was a relationship between acceleration and position. We saw this for an example of, say, Hooke's law, ma equals minus kx. That was an example where you could relate acceleration to position by some physical constants. Now I could even throw an m here just to and then get rid of this. Call it something like k. So then you can think of this. The left-hand side is ma. So then the right-hand side is, in this case, just a single restoring force from a spring. If I add dampening might look something like this, where there might be some additional term that's involved. Force that's dampening might be something that goes as minus bv. Trudging through honey, or when you're moving at very slow speeds through the air. The drag that you experience is some constant multiplied by your velocity. The faster you're moving, the more air drag you experience. Until your velocity is brought to zero. It's always acting in the opposite direction of your velocity, which means it's always acting to slow down the object. This is sometimes called Stokes drag, when it goes as v to the first power. There's also Newtonian drag, where it goes as v to the second power. And that's like when you're going through air. Airplanes have to worry about Newtonian drag, these sorts of things. If I were to, and again, remembering that velocity is the derivative of position, I could write it as I did on the left-hand side, with this additional term, which dampens the system. It acts to bring everything to rest. In a differential equations course, you could actually solve this. I could figure out what x as a function of time is. I will just write down the solution. X as a function of time contains the simple harmonic motion. You can still write it as something like this. But on top of it, it is all multiplied by e to the minus, I think it's bt over 2m in this case, where omega is, again, root k over m. And the amplitude depends on your system, how you set things up. So there's the simple harmonic motion component, but then there's this overall exponential, which exponentials, e to the negative number, the larger you make, the larger time gets, that entire exponential, it gets smaller and smaller and smaller. So the motion damps down and everything damps down to the equilibrium position. So where is my applet to show that? There we go. So this is showing oscillating motion as a function of time. Again, the gold dashed line is going to be just purely simple harmonic motion. The blue line is going to show what happens as I increase the amount of friction. This is called F. I should have called it B. Can I change that actually real quick? Is that going to screw everything up? Not that it really matters. Let's see if this breaks everything. Okay, there we go, B. So the idea is that as I increase B, we can look at what the new solution, the solution with friction, looks like compared to simple harmonic motion, which is the gold dashed line. So with no friction, they're both exactly the same. As I give it a little bit of friction, notice what happens. Initially, it looks quite the same. Doesn't quite make it as far down as it would have without friction. So friction has impacted it a little bit. And then it turns around and swings back up as simple harmonic motion does. But now it doesn't, this distance has increased. Then it goes back down again, and this distance has gotten even bigger. This is much a bigger difference than it was here. And this is a smaller difference than it is here. It gets worse and worse and worse. I could even increase friction to make this more obvious. As friction damps away the motion, the oscillation still occurs, but it eventually comes to rest. This is called underdamped oscillatory motion. The friction is non-zero and present, and eventually everything will slow down, but you still get oscillations. You still get an oscillation that causes the thing to bounce back and forth. It just bounces back less every time. I could slowly but surely increase the friction, and you notice that the ripples are all converging towards the origin. There is a point right about here where the motion stops oscillating. Instead, it just plummets down to the origin, and that's it. Where when it was a little bit smaller, it overshot, in this case only once, and then came back up and then went to the origin. But there's some critical point where the oscillations do not ever occur. There never is a full oscillation. It just quickly damps down to zero, and you just immediately are brought to rest. This is called critical dampening. Doors are designed, doors, you might notice, when you pull them open, you feel a little bit, you feel a force, it's not completely easy to open the door. And then doors are designed so you can't slam, doors of like stores and like office buildings and whatnot. You can't slam those doors. If you tried to slam the door, it would slow down as it was brought and then would slowly but surely close. For doors that are, automatically close when you let go of them. My office door is not like that, so I cannot demonstrate that. But the doors, of office buildings and whatnot, where you can open it and when you let go, it will return itself to an equilibrium position in this case, of it being closed. Those hinges are designed, for energy efficiency reasons. They are designed to bring the door to a close as quickly as possible, but you don't want it to oscillate or overshoot, because then it would run into the door frame and that might damage the door frame. You want it to very quickly, but not, crash into the door frame, but nonetheless very quickly be brought to a close. So door hinges that automatically close are designed, they tweak the values of, say, the spring constant and the dampening force, such that the door hinges themselves are critically damped. This allows the door to close very rapidly, which can be important if it's a building, say, that is maintaining heat or air conditioning. You don't want that energy to go outside because that's waste. You might think, what if I increase friction even more? And here it's a little bit non-intuitive because if I increase friction even more, the curve is brought back up. It takes longer for the object to get to equilibrium when there's too much friction compared to when it's critically damped. And it's brought to a close very quickly. In this case, there is so much friction that right, it really, the idea of oscillatory motion really breaks down. It's more like, a box sliding down an inclined plane or something like that. The restoring force is essentially completely negated and counteracted by the friction. Essentially, the friction is more than, just barely less than the restoring force, which, so as a result, the acceleration that brings it to a close or to the equilibrium point is very slow. So it takes a long time for the object to ramp down to zero. Compared to this case where you have the restoring force really trying to pull the object towards the origin, and it does so with ease, but there's just enough friction so that friction ensures that it only does that once. So that's damped motion. The kind of motion I think is more fun to think about is driven damped motion. So you might have a restoring force that makes things want to oscillate. You might have a friction term that makes things, not oscillate forever. But maybe you also have some sort of driving force, some function of time that is trying to drive the system in a certain way. An example could be you take your cousin or your baby cousin to a park, and they're on a swing. Them just on the swing, not moving, they would oscillate, roughly simple harmonic motion, depending on how high they're oscillating. But occasionally, you might also push on their back to give them a little push, and that, of course, then changes the resulting motion. So they're undergoing some sort of oscillatory motion, but then occasionally you will provide an external force to the system that drives the system at some rate. Maybe it's individual impulses, like you pushing someone else on a swing. Maybe it's a glass that is constantly being exposed to repetitive forces from, say, the sound wave of an opera singer pushing on the glass. And that wave, that sound wave, is which again is a wave, that's where we're about to get to, is constantly impacting the glass. So you could have some sort of constant force or a constant oscillatory force that's impacting the system. So I think I have a movie of this. Yes. Make use of high shutter cameras. So the idea here is that, the idea here is that they're taking very high frame rate images of a wine glass as being exposed to a sound wave. So a sound wave is there's peaks and troughs of that sound wave. So you can think of the peaks and the troughs as moments of high impact. There's lots of kinetic energy associated when you're at the top of the wave or the bottom of the wave, compared to when you're in the middle of the wave. So you can think of that as where you're receiving large amounts of energy and low amounts of energy. No. So in this case, what you're seeing is that there's a driving force that's causing the wine glass to oscillate, as a result. And if we speed it up and slow it down, I guess, I think they show the sound wave, right? The idea of the sound wave is kind of pushing, and you can think of high energy transfer, low energy transfer with the colors that you're seeing. And so the colors are kind of oscillating, showing that you're constantly kind of pushing, like the kid on the swing, you're constantly pushing the kid on the swing with some sort of repetitive force that's being driven in this case. Now we can think of what could possibly happen. Take the example of the kid on the swing. I think that's the easiest one to imagine. If there was a kid on a swing, their resulting motion is different if you randomly push them, if you randomly, sometimes when they're at the top, sometimes when they're in the middle, sometimes when they're far back, if you randomly picked points to then push the person on the swing, that motion would look very different compared to if you always push the person on the swing when they were down back at you at rest, and that's when you push. You're pushing, in that case, in the direction that the restoring force is also trying to move the person. When they're way back and you're pushing them forward again, gravity and torque really is also trying to make the person swing forward, but then you're also additionally pushing them forward, so you're helping the restoring force every time you push someone when they're at the back of the swing, compared to if you were to push them at some other point, where you might be working with the restoring force, or you might be applying a force that's in a different direction than the restoring force. In that case, in the case of you randomly pushing, the motion is chaotic and they might even be brought to rest at some point. But if you're always pushing the kid when they're at the back end of the swing, you notice that they get higher and higher. You essentially are driving them to have higher amplitudes because you and the restoring force are working together when you apply that force. A physicsy way of saying that is that you are applying a force that is in sync with the natural frequency of the oscillator. There's a natural frequency that the kid on the swing is swinging at, and you happen to be also applying a force at that same natural frequency, such that you and the restoring force are always working together every time you give the kid a push in the back. Remember, natural frequencies are a result of the physics of the system, the length of the pendulum, the mass of the box, things like that. All objects, in a sense, have a natural frequency. Going back to the ideas of, that there's natural frequencies attached to individual molecules and atoms and things, there's a natural frequency of, say, this table. If I were to bang on the table, while I cannot see it because the table essentially has an enormous spring constant, I just created a wave that rippled through the table. The table oscillated a little bit at its natural frequency. Every object has its own natural frequency. If I stretch my skin and release it, it restores itself, and really it oscillated a little bit. It was very highly damped, so my skin just immediately kind of returned to its original position. But nonetheless, there's a natural frequency associated with the atoms and molecules that make up my body, make up a wine glass, make up any sort of material. So the idea behind the opera singer breaking the wine glass is what they are doing is they are emitting a tone that is the same frequency as the natural frequency of the object. And you can kind of see this here once it gets going. Essentially, the blue color is always hitting the back of the wine glass when the wine glass is also farthest back. Where again, that means the restoring force, right? The glass wants to be circular. But it's in this kind of weird, distorted shape, so it wants to restore the top and the bottom of the wine glass to be back to being closer to the center and making this entire thing circular. But every time it's way back here, like a kid on the back of a swing, it's then getting an extra push from the sound wave. And if you adjust the sound wave so that you're always doing this in resonance, in sync with the wine glass, that causes, like the kid on the swing, you're pushing it more and more and more. That causes the oscillations to grow in amplitude, and eventually the wine glass breaks. Striking this resonance with the natural frequency. It's kind of fun with wine glasses. Though I never quite understood the opera singer. The last thing I'd want to do is to hold my mouth wide open right in front of a glass that I know is about to shatter into pieces. But this also has consequences. This leads to, I should have brought up a photo of, natural frequencies being hit by, say, bridges that then collapse as a result. This was in not San Francisco. What was it in San Francisco? The Tacoma Bridge. Where is the Tacoma Bridge? Oh, it's nowhere. It's not even in California. What am I thinking? It's in Washington. I'm trying to find an image. There we go. Thank you, Wikipedia. Right, the idea that this Tacoma Bridge like underwent extreme oscillations because of issues. More also had issues with torsion. Essentially, the wind struck a resonance with the bridge, and then that led to some torsion forces that ended up being problematic for the bridge. I thought there was a movie of this.
Hello there. Are you
hello.
sleeping on a nectar mattress, or are you sleeping on a piece of garbage? Not sure?
Not sure. There we go. Let's turn off this dramatic sound, though. Right, the idea that this natural frequency was struck in the bridge, which led it to start to rotate and twist as a result. They seem very calm. If I were to see this, I'd be terrified. But this ultimately led to the entire structure eventually breaking down, and the entire bridge collapsed as a result. A result of, like the wine glass, like the kid on the swing, eventually it was being, resonated at the natural frequency of the system. So you want to avoid driving things at the natural frequency of the object, because it leads to no good. I can show an example of this. So this might be a little bit hard to visualize, but this should give you the right idea. So here I have damped oscillatory motion, that's the blue curve, as a function of time. So it damps to some zero value. I'm also applying a driving force. I'm driving the system, and I'm going to drive it at also a sinusoid. So the dashed yellow curve is showing you the force that I'm applying also to the system. So in this case, I'm applying just a constant force. The restoring force is trying to bring things to zero, but there's a constant force that's trying to push it away from the origin. In this case, dampening gets rid of the oscillation, and eventually the thing reaches some sort of equilibrium where the restoring force is perfectly in balance with the driving force. Like spring force pulling up and gravity pulling down. There's some balance point where the forces are in balance. That's the same idea here. And the motion will die away and then just be stuck there. And notice that the natural frequency of the system looks like it's about like 3, or the period is about, say, 7 seconds or so. Now if I change how I drive the system, so here I'm just doing very long, gradual, I'm sometimes pushing and pulling and pushing and pulling very slowly on the system at a frequency that's much lower than the natural frequency of the system. So I'm doing this, the period in this case is like 15:30, so the period is about 15 seconds versus the natural frequency, which was closer to like 6 or 7 seconds. So in that case, the oscillation looks kind of weird. It wobbles a little bit, and dampening is bringing down the oscillation, and eventually it might actually just come to rest, and then it will just like flow along with my backward and forward oscillating motion. If I increase this a little bit more, notice what's happening. There are cases where I'm driving the system up and down, and sometimes I'm working with the restoring force. Sometimes I'm working against the restoring force. So sometimes, you sometimes get moments where everything is working together. You get a really high amplitude and a really high amplitude here. But then sometimes they're not quite working together and the amplitude decreases. The restoring force and the driving force are canceling each other out. Sometimes they're working together. But I continue to increase. Notice this does not look good. Now we're getting to a situation where I'm getting very close to the natural frequency of the system, which I think in this case is omega of 1. And notice what's happening to the amplitude here. Let me try to go out a little bit farther, actually. Let me go out to 50. Right, so in this case, it's getting, or in this case, it seems the oscillating motion is sometimes working with the driving force. Amplitude is getting even bigger. Then it goes away a little bit, and then essentially we'll go between these regions. So this would be the bridge kind of really wobbling. But there would be some peak. It would only go so high. But if I were to increase this even more, now I'm approaching the natural frequency, which is unity. Notice what's happening here. I'm essentially oscillating the system. I'm driving the system at the natural frequency. I'm singing at the note of the wine glass. I'm always pushing the kid when their back is, when they're at the back of the swing. And so as a result, the amplitude gets bigger and bigger and bigger and bigger. And if I did this at exactly 1 and zoomed out in time and zoomed up and down in the vertical axis, this wave would just get bigger and bigger and bigger as a result. The amplitude would grow without bound, in a sense. This would be completely, unstable oscillatory motion. Then what happens when you start to oscillate faster than the natural frequency? Then you get the same sort of thing where you are essentially you're oscillating, you're driving the system really, by oscillating it up and down really fast, which is much faster than the natural frequency. So essentially, in that case, everything averages out. Essentially, you're always working, you're working with and against the restoring force, essentially in equal amounts. And so it reaches some sort of balance, some stable equilibrium where essentially everything gets damped away. Nothing really quite happens when you're driving at a frequency that's higher than the natural frequency. So it's frequencies that match the natural frequency, which is dangerous. All right.